Hello class, welcome to the Stat 215 Lecture 14 video. In this video we're going to continue our discussion about the normal distribution. So first we want to talk about how we can use z-scores to calculate probabilities for any normal distribution. Second, we're going to find percentiles for any normal distribution. And third, we want to identify the nature of the relationship between the normal distribution and the binomial distribution. If you think back to a couple lectures, we talked about the relationship between the binomial distribution and the binomial distribution. Well, we're now going to do something similar with the normal distribution. So let's get started by looking at our first objective, using z-scores to calculate probabilities for any normal distribution. So if we think of last time, we used the 68, 95, 99.7 rule to find approximate areas for a normal distribution with any mean mu and any standard deviation sigma. We also use the z-table to find areas for the standard normal distribution, which if you recall, the standard normal distribution is when we have the mean of 0 and standard deviation of 1. In this lecture, we're going to use the z-table to find the areas for any normal distribution. So in order to do that, we need to start by learning and discussing about z-scores. So we can convert a probability about any normal random variable x with mean mu and standard deviation sigma to a probability about a standard normal variable z using a z-score. So a z-score is equal to x minus mu divided by sigma. And what a z-score does is it actually converts your normal distribution that you're currently working with into a standard normal distribution. This is particularly handy when we're working with something that we want to compare something that has different units, say time in feet. One popular example is if you think of a track meet where you have people running the long jump and then you have people running a race. Long jump, we measure that in distance, where when they're running a race like a relay, it's measured in time. So if you want to compare who's really the best athlete when we're measuring someone who's long jumping and running, what we can do is we can convert their scores into a z-score, and that will give them the same units, so to speak. So what a z-score does is it indicates how many standard deviations the value x is away from the mean of its distribution. So a z-score of, say, 2.34 is actually saying that x is 2.34 standard deviations above the mean. And a z-score of negative 1.56 says that x is 1.56 standard deviations below the mean. So what we do is, regardless of how your original normal distribution is, we convert it into the standard normal distribution and we put it in terms of like the units in terms of standard deviation. So transforming our x to z, so if you have a random variable x and it has a normal distribution with mean mu and standard deviation sigma, then the random variable will be z equal to x minus mu over sigma. And this will now have the standard normal distribution. So let us say we have x1 equal to x1 minus mu over sigma, and z2 equal to x2 minus mu over sigma. Then we could find the probability of x1 less than x2, which would be equivalent to 1 over the square root of 2 pi multiplied by sigma times the integral from x1 to x2 of e to the negative 1 over 2 sigma squared multiplied by the quantity x minus mu and quantity squared dx. This is going to be equivalent to 1 over the square root of 2 pi multiplied by the integral from z1 to z2 of e to the negative 1/2 z squared dz, which is equivalent to the probability of z1 less than z2. Now, I understand if this may not have made complete sense to you, so let's take a look at it visually. So what we are essentially doing is this first graphic, we'll call this graphic A, this first distribution. this was our original normal distribution. We had our mean mu, and we wanted to find the probability of x1 less than x less than x2. What we did was we can convert it to the standard normal distribution, which we can call our distribution B, where we have our mean 0, standard deviation of 1, and we will find the area from Z1 to Z2. These shaded areas are equal, which is why we can do this. So to help things out, let's start by taking a look at a first example. So let us have x be following the normal distribution with mean of 6 and standard deviation of 2. And we want to find the probability that x is less than 3.4. So what we can start off is by finding its z-score. So z will equal x minus mu over sigma. By plugging in, we will have 3.4 minus 6 over 2 equals negative 1.30. This means that 3.4 is 1.30 standard deviations below the mean of 6. So in terms of probability, that means that what we were trying to find, the probability of x less than 3.4 is equivalent to the probability of z less than negative 1.30. And we have a visualization to show you how we have made these two equivalent. So now at this point, finding the probability of z less than, I believe it was what, negative 1.30, we can now use our z-table. Again, we want to find the probability of z less than negative 1.30, negative 1.3.0. That will give us a probability of 0.0968. So the answer to what is the probability of z less than 3.4 is going to be 0.0968 or 9.68%. Let's take a look at a second example to help further understand this concept. So let x follow the normal distribution with mean 10 and standard deviation of 1.5. In this case, we want to find the probability that x is greater than 12.2. So first step is we're going to convert this into our z-score. So z will equal x minus mu divided by sigma. So we'll plug in, so it'll be 12.2 minus 10 divided by 1.5, which will give us 1.47. What this means is to find the probability of x is greater than 12.2. This is going to be equivalent to finding the probability of z greater than 1.47. Now, if you recall, the standard deviations, wrong word completely. When we're finding probabilities using our z-table, remember those probabilities are for the area to the left of the curve. So we can't find directly the probability of z greater than anything, but by using our complement rule and doing 1 minus the probability of z less than 1.47, we can find the probability. So in order to do that, we will use our z-table, and we will have 1 minus 0.9292. I'll leave it to you to look this value up on the z-score, but trust me, I'm right. And we will get a final answer of 0.0709. Okay, now let's take a look at a third example. So for this one, let us say x follows the normal distribution with mean 50 and standard deviation of 10. In this case, we want to find the probability that 45 is less than x is less than 62. Okay, so this is going to require us to find two z-scores. So first, our z-score 1, which I'm going to change the color on this just because I understand that green is probably a little bit harder to see. So z1 we'll have this be x1 minus mu over sigma. And we will have 45 be equal to x1 and 62 be equal to x2. Plugging in, this would be 45 minus 50 divided by 10. This will equal negative 0.5. And our z2 will be x2 minus mu divided by sigma. So 62 minus 50 divided by 10, and this will equal 1.2. So for us, this means that the probability of 45 less than x less than 62 is now going to be equivalent to the probability of negative 0.5 less than z less than 1.2. And if you recall from our previous classes when we've been working with these tables, when we were trying to find the probabilities between two values, we have to change this to be the probability of z less than 1.2 minus the probability of z less than negative 0.50. Using our z-table, we will get the probability of z less than 1.20 to be 0.8849, and the probability of z less than negative 0.50 to be 0.3085. And again, these two values come from our z-table. And this will be equivalent to 0.5764. So the probability that 45 is less than x less than 62 is 47.64%. Very good. Okay, so let's move on to the next example. So a certain type of storage battery lasts, on average, 3 years with a standard deviation of half a year. Assuming battery life is normally distributed, find the probability that a given battery will last less than 2.3 years. So we are given that x is going to follow the normal distribution with mean 3 and standard deviation of 0.5. We are asked to find the probability that a given battery will last less than 2.3 years. So this is going to be equivalent, if we use our z-score, to 2.3 minus 3 over 0.5. So notice what I did there is I just went ahead and put the z-score formula and all of its parts right into my equivalence statement. And now I'm going to simplify. So this will be the probability of z less than negative 1.40. And if we check our z-table, that will be 0.0808. Perfect. Easy peasy, right? Well, let's keep going. And take a look at example 5. So in an industrial process, the diameter of a ball bearing is an important measurement. The buyer sets specifications for the diameter to be 3 plus or minus 0.01 centimeters. No part falling outside of these specs will be accepted. If it is known that the ball bearings produced by the process have diameters that are normally distributed with mean of 3 and a standard deviation of sigma equal to 0.005, what percent of manufactured ball bearings will be scrapped? Okay, so we are given, whoops daisies, we are given that x is going to follow the normal distribution with a mean of 3 and a standard deviation of 0.005. And we were told that it would be scrapped if x was less than 2.99 or if x was greater than 3.01. Now, this is the important bit. Since our distribution is symmetric, that's going to mean that the probability of x less than 2.99 is going to be equivalent to the probability of x being greater than 3.01. And I'm going to rewrite this because I wrote that very sloppy. Which means, luckily for us, we will just need to calculate one z-score, find that probability, and then multiply it by 2. So let's do the z-score for 3.01. And why did I do that? Well, because this one's actually the harder one, and I figured it's good practice. So we'll let z equal 3.01 minus 3 over 0.05, which will equal 0.01 over 0.005, which will equal 2. So the probability of x is greater than 3.01 is going to be equal to the probability of z greater than 2. Remember, with our z table, finding z greater than something, we cannot do directly. We have to use the complement rule and find 1 minus the probability of z less than 2, which is why I did this one. The other one, we could have done it more directly. This will be equal to 1 minus 0.9772, which will equal 0.0228. So to find our total percent scrapped, we are going to, as I said before, we're going to multiply our probability of just one direction, which is the 0.0228, and multiply it by 2 because it's less than 2.99 or greater than 3.01. So this is going to be equivalent to 0.0456 or 4.56%. So the chance of the metal being scrapped is at 4.56%. Very good. So at this point, I feel like we did a pretty good with Objective 1. Let's take a look at Objective 2 and find percentiles for any normal distribution. So using our normal curve in reverse for any normal distribution, we now know how to find z such that the probability of z less than z equals a specified probability. Now we want to find x such that the probability of x less than x equals a specified probability. We have that z is equal to x minus mu over sigma. If we rearrange this equation and solve for x, we can see that x is equal to sigma multiplied by z plus mu. So this means that we can find the value of z that gives us our specified probability you want, and then use this formula to convert z to x. Let's take an example of this to show you how this works. So let x follow the normal distribution with mean of 40 and sigma or standard deviation of 6. We want to find x such that the probability of x less than x is 44%. Okay, so first, we're going to need to find the probability of z less than z that equals 0.44. We did this in our previous lecture. And so using our z table, we would have found z to be negative 0.15 which is honestly an approximation, because actually it's the probability of z less than negative 0.15 is actually 0.4404, but that's as close as we were able to get. Now at this point, we can use our new formula of x equals z times sigma plus mu. Our z is negative 0.15, our sigma is 6, and our mean is 40. So this is going to be equal to 39.1. And there we have it. What do you think? Easy? Well, let's find out. Let's do another example. Suppose SAT scores are normally distributed with a mean of 1068 and a standard deviation of 210. What score do you have to earn to be in the top 20%? All right, so we will assume that x follows the normal distribution with a mean of 1068 and a standard deviation of 210. We are going to want to find x such that the probability of x less than or equal to x equals 0.80, which means we need to find z such that the probability of z less than or equal to z is equal to 0.80. So if we take a look at our z table, we're going to want to get to as close to 0.80 as possible, which by my standards, that would mean that z is going to be equal to 0.84, because our probability of z less than or equal to 0.84 was equivalent to 0.7995, and that's going to be about as close as we can get. You'll notice that I have not been pulling up the z table in this lecture video. That's something I'd like you to practice on your own. If you end up having problems, please send me an email and we can work through it. But I'm hoping that the last lecture video would have had you comfortable enough with the normal table that I don't need to be flipping back and forth. But again, if you're having problems, send me an email. I'd be more than happy to work through it with you. Okay, so back to the problem. So we found our approximate z-score, or at least as near as we can get. That means we can now plug into our formula of x equals z multiplied by sigma plus mu. Now's our moment to plug and chug. And we will get an answer of 1244.4, which I know realistically, if I remember correctly, we do SAT scores are not a fraction of a point, so we'll just say that means you need to score a 1244 in order to be in the top 20%. Very nice. Okay, so that seems to be pretty good. So now we can move on to our third objective. We'd like to identify the nature of the relationship between the normal distribution and the binomial distribution. So to start this off, we're going to need to know a theorem. So if x is a binomial random variable with n trials and probability of success p, then x minus np, which you may recall np is the mean, divided by the square root of np multiplied by 1 minus p, which you sometimes know as q, can be converted into our standard normal distribution as n goes to infinity. Where this has its application processes is if x is a binomial random variable with n trials and a probability of success p, then we can calculate the probability of x less than or equal to x equal to the probability of z less than or equal to x plus 0.5 minus np over the square root of np multiplied by 1 minus p, where NP and N times 1 minus P are greater than or equal to 5. You may be wondering what this 0.5 is and why we added that in. That's a continuity correction. It's beyond the scope of this course, but if you're curious, you're more than welcome to Google it, but you don't actually need to understand why that 0.5 is in there for this course. So let's take a look at what this does. So the distribution of a binomial x with n equal to 15 and p equal to 0.4, that'll give us an np equal to 6 and an n times 1 minus p equal to 9. So we have that np and nq both greater than or equal to 5. So if we were to do this and graph it out, you can notice that the graph of what have been the binomial distribution looks very similar to the normal distribution. And that's going to be true, as we'll see in later classes. We're going to talk about something called the central limit theorem. But basically what it means is for certain distributions, as their sample size increases, they basically convert themselves into the normal distribution, or they begin to behave and look like the normal distribution. So let's take a look at an example of this. Let x belong to the binomial distribution with n 15 and p equal to 0.4. And we know that the probability of x less than or equal to 4 equals 0.1273 from the binomial CDF table. Now let's see how this applies, how close we can get, I should say, if we do the normal approximation to the binomial. So let's say we're going to, again, do the probability of x less than or equal to 4. This will be equivalent to the probability of z less than or equal to 4 plus 0.5 minus 15 times 0.4 all over the square root of 15 times 0.4 times 0.6, which if we all simplify that together, this will be the probability of z less than or equal to negative 1.5 over the square root of 3.6, which will be equivalent to the probability of z less than or equal to negative 0.79, which at that point we would use our z table and we would get the probability to be 0.2148. So you can see it is an approximation. It's not going to be equivalent, but it will be close. Why would you use this? It depends on the situation you're in. When we're working with larger numbers, sometimes it's easier to work with the standard normal distribution because it has so many nice properties applied to it. Let's take a look at example 9, and I promise this is the last example of the lecture. So the probability a patient recovers from a rare blood disease is 25%. If 100 people are known to have contracted this disease, what is the probability that fewer than 30 people survive? So we can let x follow the binomial distribution with our sample size of 100 and our probability of success being 0.5. This will imply that our NP is going to be 25 and our NQ, remember, Q is equal to 1 minus P. I'm most comfortable using Q as opposed to 1 minus P. I think it looks neater, but it's a personal preference. And so NQ would be, in this case, 75. We want to know what is the probability of x being less than 30. Now, because, again, this is talking about the binomial distribution, which is a discrete distribution, so we can't actually do x is less than 30 directly. We have to do the probability of x less than or equal to 29, which now we will convert into our z-score. So this will be z less than or equal to 29 plus 0.5 minus 100 multiplied by 0.25 over the square root of 100 multiplied by 0.25 multiplied by 0.75. this is going to be equivalent to the probability of z less than or equal to 4.5 over 4.33. So simplifying one more time, this is going to be the probability of z less than or equal to 1.04. If we check the z-table for 1.04, we will get 0.8508. Now, at this point, you're saying, okay, this is the approximation. I know from the previous example, this isn't as close as I maybe want it to be. Well, just so you know, if you were to say plug this into R or some other statistical software, or if you really wanted to go ahead and calculate it by hand, if we wanted to find out using the exact for the binomial distribution, this would have been 0.8505. So like I said, this is still pretty close, but it's certainly a lot easier to use the z-table approximation than trying to directly calculate the binomial distribution. Okay, so that's it. Let's just summarize what we've done in this class, and then that will be the end of this lecture. So what have we done? Well, first we used a z-score to calculate probabilities for any normal distribution. We talked about how to calculate the z-score, being z equals x minus mu over sigma. We then manipulated or arranged that z-score formula to calculate that x equals z multiplied by sigma plus mu to find percentiles for any normal distribution. And then last but not least, we used the normal distribution to approximate binomial probabilities when NP and NQ were greater than or equal to 5. All right, that's it. Have a good night. And as always, if you have any questions, please send me an email.